from Ohm's law, which is V is equal to IR. What is the important term after this? It is resistance. Usually, when we introduce Ohm's law, we told that R is resistance and it's a constant value, remember? But resistance actually is not a simple term as that of a constant. It has very significance. Why I'm saying significance? So, what happens when a resistor or conductor is connected to a supply? Usually the conductor has a lot of free electrons, and when it is connected to a supply, an electric field is generated, and we know that electrons is going to move towards a positive terminal, and the negative terminal of the supply is pushing the electrons, or I will say accelerating it towards the towards the conductor or the next section, right? This much you have cleared, or I have taught you guys. So when this is happening, the electrons are very randomly moving towards each other, and they are colliding with each other. When they are colliding, they lose their existing energy which they had. When they lose energy, that means they cannot further move. When they are not going to move further, that means the current is going to reduce, right? Because current is due to the flow of electrons. When the flow of electrons reduces due to the less energy formation, that means the current is reduced. When current is reduced, I say there has been an opposition in the flow, right? And that opposition is known as resistance. That is I can say the least, or I can say is the most proper explanation in terms of electron level. Clear? This much you know. So what happens is, in resistance you require an equation, right? From this equation I can write V by I is equal to R, right? So I'm going to derive an expression which you have learned in the 10th class, I believe. So how that expression came, we will discuss here. So V, in place of I am going to write it, the current in terms of drift velocity, that is NEA VD, right? So V divided by NEA. VD we have derived in the last section of the previous video. It is E tau by M. Please look into that part, right? This is the expression. Now what happens, this M can go up, so it becomes Vm. Then there is N into E squared, right? So there will be N E squared, right? Then there is A, then E tau. This much is clear. Now can I write V in somewhere else, or I can write V is equal to what? E into L. This you have tried, or you have learned, that is E is equal to dV by dr. Remember, minus is there, we are going to neglect it because electron is also negative. Let's not take it, we are just considering the magnitude. So these are all our modulus values. So dV will be equal to E into dr. dr is a distance, right? From where to where the electron is moving, it is moving throughout the conductor. So this dr becomes L and dV becomes V, right? From this expression I can write V is equal to EL. I'm going to substitute that value here, divided by NE squared AE tau. So I can cancel E. So you will get an expression. See, I'm going to arrange some terms in one section. M NE squared tau, and there is L and there is A. This much is clear. And this is what expression? What's expression? It is the expression of resistance, right? Hope you guys have remembered in 10th class you have studied this expression, R is equal to rho L by A. So the same expression is coming here, right? So this much term, that is M divided by NE squared tau, is the expression where the entire material or the entire parameters, that is mass of the electron, N number of electron, E charge of the electron, tau relaxation time of the electron, are all depending upon the material, right? And that terms combinedly are being replaced by a single constant term, and that is known as resistivity or specific resistance of the conductor, right? From this expression only this equation came up, which you learned in your 10th class, right? So you are introduced with a term called resistivity. So resistivity of a material is something, or the parameter or the character of the object with which the conductor is constructed. It depends upon mass of the electron inside that conductor, number of electrons, charge of those electrons, and relaxation time. So as you can, after we understood the expression of it, we'll deal with resistivity now in details. Okay, now resistivity is something as the term indicated, it depends upon mass, number of electrons, E, charge of the electron. But there is an extra term which is rho. Tau. Tau means relaxation time. That is not something which is fixed. It changes, right? And the major criteria on which it depends is temperature. So depending upon temperature, how rho is going to change, we are going to take that in detail. What? Temperature dependency of rho. Now first is I have drawn the graph earlier. This is for good conductor. Right. What happens in the case of good conductor? For good conductor, as the first graph indicates, rho is directly proportional to temperature. That is, as the temperature increases, resistivity also increases. Of course, as the temperature increases, the initial condition, okay. Now, but the some scenario when the temperature is very, very low, that is, it is much more lesser than 0 degrees Celsius. On those conditions, the graph is not linear. It is found experimentally. Okay, so when you saw at lower temperature, right, the resistivity is not increasing as that speed, or resistivity is varying in a different way, in a non-linear way. This much clear? And there is an equation, guys, which you have to learn or by heart. So that is which gives an exact derivation or exact explanation of resistivity and temperature dependence for almost all the material, but it is much more true in the case of a good conductor. That is rho T, that is temperature. Resistivity at a temperature T is equal to rho R, that is reference temperature's resistivity, into 1 plus alpha into Tt minus Tr. Right. This is the basic equation where you explain resistivity's dependence. I will tell you. Suppose there is I am giving you an example, okay? Suppose at temperature, reference temperature, that is at 15 degrees Celsius, it has a compound is having a resistivity of, I'm just giving an arbitrary value, okay, 0.01. Right. At you're asked what will be the resistivity at a temperature of say 35 degrees Celsius, and you are given alpha. What is alpha? That is coefficient of temperature, or temperature coefficient of resistance, a constant term. Okay, alpha is temperature coefficient of resistance, and it is given as suppose 0.005 or 0.5, whatever. I'm just giving an arbitrary value. So your question is, at 35 degrees Celsius, what will be the resistivity? If at 15 degrees Celsius, the resistivity of that material is 0.01. You just have to substitute. You are fast. What is resistivity at 15 degrees Celsius? So this is your rho 15, suffix 15. That is equal to, at R, reference. What has been given as a reference? At 15 degrees Celsius. So rho at 15. 1 plus, what is alpha? 0.05. And what is temperature? Given temperature, you don't know. Yes, you are given, that is 35 degrees Celsius. What is the temperature given as reference? That is 15. You calculate the value, you put the value here. Rho 15 will be how much? Is given 0.01, sorry, 1 plus 0.05. This will be what? 20. You will get a particular value, but how much it will be? Rho 15, I'm going to, it will be 1 plus 0.05 into 20, it will be 1, right? 1 plus 1 will be 2, 2 into 0.01 will be 0.02. This will get an answer at this much. So that is at 15 degrees Celsius, if the resistivity it is 0.02, at 35 degrees Celsius, the resistivity became 0.02. I hope you understood why this problem was done, right? So you are indicating a constant term here, which is alpha. I can generate the equation from alpha from the same equation. This is alpha is equal to rho T minus rho R divided by Tt minus Tr. This is an expression for temperature coefficient of resistance. It is derived from this expression itself. This expression should be by hearted, guys. Problems are usually asked from this. Clear? So in case of a superconductor or good conductor, at higher temperature, rho is directly proportional to temperature, but lower temperature, linear dependency doesn't come up. And usually rho is less or least value or very small in the case of a what? Superconductor. Now we'll move on with alloys. Right, alloys. alloys, I know, I hope you understand what is alloy. Is a combination of many metals. In this case, rho is very large, resistivity is very large, guys. Right, so usually, so when you draw a graph with the rho and t, it never starts with 0, it usually starts with the middle point, and it has least temperature dependence in the case of alloys. Right, now similarly we will go with the third criteria, that is semiconductors. You will learn about semiconductor later on chapter. When a graph is plotted between rho and temperature, the graph is in this way. Right, and the expression is also different. This and all equations are not there in your NCERT book, guys. I'm just indicating this because sometimes it might be asked in your NEET or JEE. And rho t, it will be not asked as a problem, it might be asked as a graphical representation or just an equation. Rho r, right, into e raised to minus eg by kt, right, where eg is the energy gap, k is Boltzmann constant, and t is the temperature. This much you know. Rho t and rho r, etc. I have explained what it is. Right, Eg is the band gap, K is Boltzmann constant, and its value is 1.38 into 10 to power minus 23. This much is clear. So this is the temperature dependency of resistivity. Similarly, there is a resistance temperature dependency also. See, we wrote an expression like this, right? What was the expression? Rho t is equal to rho r into 1 plus alpha into tt minus tr, right? Similar expression is there for resistance also, that is RT is equal to RR 1 plus alpha into TT minus TR. That is, I will do an example with here. Suppose at 15 degrees Celsius the resistance is 10 ohm, and you are asked what will be the resistance when the temperature is 35 degrees Celsius, and you are given alpha as 0.01. Your problem will be like this. So you just have to substitute RT, I don't know. You are asked to find temperature, means which temperature? 35 degrees Celsius. RR at 15 degrees Celsius, the reference temperature, I am given resistance as 10. 1 plus alpha is 0.01. RT temperature is 35 minus 15. I hope you can do it later on. I hope you understood the scenario. Clear? This much is clear? Right, so this is how the temperature is going to change resistivity and resistance of almost all the materials we have discussed. Clear? What is the unit of resistivity? What is the unit of resistance? I hope you remember, it is ohm, right? So similarly, what is the resistivity's unit? Rho. I hope you know that also. You might have learned rho unit in 10th class. I don't know if you know it. Say R is equal to rho L by A, right? From this I can generate rho, that is A R by L, right? Area's unit is how much? Meter squared. Resistance unit is ohm, and length unit is meter, so it will be ohm into meter. So ohm meter is a unit of rho or resistivity. Right, so I can even give a definition of rho from this equation, that is, if, see what happens when A and L is 1, what happens when A and L is 1, then there will be only R, so rho will be equal to R, right? Hope you understood. This and all are very simple, guys, that's why I am speedily telling you. When R is 1, sorry, when A is 1 and L is 1, then R will be equal to rho, because this is the expression for rho. Now that means in definition, the conductor is said to be having resistivity of 1 ohm meter when the conductor is having an area of 1 meter squared and length of 1 meter, right? Or I can say when the length of the conductor and area of the conductor is equal to 1 unit, then the resistivity is equal to the resistance of the wire. This is the proper definition of resistivity. Clear? Clear? So ohm meter is a unit of resistivity and ohm is a unit of resistance. Similarly, there is another terms, two terms, or I will say three terms which you have to learn, that is conductance, conductance, and its symbol is G, and there is conductivity, sigma, right? Conductance is the reciprocal of resistance, that is the ability of any material to allow the current to pass through it, right? So it allows. So G is reciprocal of R. So what would be the unit of G? right? 1 by ohm, or I can say ohm raised to minus 1. This is ohm raised to minus 1, or I can tell it or call it as mho, MHO. And another unit is, or another name of the unit is Siemens, or S, right? Similarly, conductivity rho is reciprocal of, sorry, sigma is reciprocal of rho. So 1 by rho's unit is ohm meter, right? So it is rho, sorry, ohm raised to minus 1, meter raised to minus 1, right? Similarly, in another unit is mho, meter raised to minus 1, or Siemens, meter raised to minus 1. These are all same units, guys. You have to by heart it. Now the third term which we want to deal, or I want to deal, is current density. This is a new one, and its representation is J. Current density is amount of current which is flowing per unit area, that is I divided by A. Unit can be written now itself, ampere divided by meter square, right? Now major question which is asked from this topic is, what is the relationship between J and rho? J, that is current density, and rho is resistivity. See, you remember the expression I is equal to, we have derived it, NE squared EA2 by M. Where I have derived, please look into your earlier topic. I am not going to tell from where. Now from here I can write it as I divided by A is equal to NE squared E2 by M, right? We have also derived an expression for N here, or rho, this NE squared 2 by M. I am not going to tell from where, look into your notes itself, right? So what, sorry, expression became wrong. Rho is M divided by NE squared 2. So here M is downwards, NE squared is above, and 2 is also above. That means it is E divided by rho. So I by A is E divided by rho, or I can say this is your current density relation, that is J is equal to E divided by rho. This is the relationship between current density and your resistivity. Clear?